Here we see photos of N2O4 in equilibrium with 2NO2 gas. This is one that we can do at room temperatures. If you have a tube of the gas and you stick it in ice, it'll be clear. N2O4 is a clear gas. As you start to warm it up, what you'll find is that it turns more yellow and then brown. NO2 is a more brown gas. So as you dip this glass tube into different containers of hot or cold, you can watch the color change. Well, let's explore the entropy of this situation. Our standard entropies are 304.3 and 239.9. As long as we're at it, let's do our delta H formations. 9.16 and 33.2. Using these values, go ahead and pause and calculate out the delta S of the universe at 25 degrees Celsius for this reaction, if our N2O4 is breaking apart into two NOs. Go ahead and pause and come on back. All right, if you're back, well, delta S of the universe is the delta S of the system plus delta S of the surrounding. And what's the delta S of the system? Well, that's just going to be the sum of the products minus the reactants. So it's going to be 2 times 239.9 for our products, minus 1 times 304.3 for our reactants. This will give us a delta S of this reaction of 175.5 joules per mole Kelvin. Does this make sense? It's a positive entropy. Well, I went from one gas to two gases. So yeah, I have more gas. The more gas particles you have, generally the more entropy your system's going to have. Gases just have the most entropy, the most freedoms of motions, as they're not tied to the other molecules, and so they should have more entropy. We see that the individual values was less for NO2, but we have two of them. So the individual molecules had a little less flex because there weren't as many atoms attached, there weren't as many vibrations and rotations available. But having two of them able to move and twist on their own versus one molecule opened up extra avenues that our starting material didn't have. So we have the delta S of the system, but now we need to know the surroundings. And the delta S of the surroundings is equal to the negative delta H of the system divided by the temp. Well, in our case, the delta H of this reaction is going to be the products minus the reactants. So 2 times 33.2 minus 9.16, which is going to be 57.24 kilojoules per mole. Plug that in, well, negative of it, so negative 57,240 joules per mole, divided by the temp, 298 Kelvin. So the delta S of the surroundings, as heat is absorbed in this endothermic reaction, as we end up more positive for delta H afterwards. It has to absorb energy from the surroundings. At this temperature, that means an entropy change in the surroundings is negative 192.1 joules per mole Kelvin. The surroundings lost heat in order to help this reaction occur, and so the entropy of the surroundings decreased. Finally, the delta S of the universe, then, is going to be the system, 175.5, plus the surroundings, negative 192.1, for a total change of negative 16.6 joules per mole Kelvin. 16.6, negative. This is not favored. Breaking our N2O4 apart into two separate NOs is not favorable at room temp. In fact, that's why we see that it's not super brown. We're not breaking this apart and making our products, or at least not very many of them. To fully discuss equilibrium and how much of the reverse reaction does happen, we'll need to get into free energy in our later videos.